Hello students, welcome to today's video. In our previous discussions, we have already discussed about the electric dipole and electric dipole moment. In this class, we have to discuss about the electric field intensity due to a dipole. Now, the electric field intensity due to a dipole can be calculated along two axes. First is the axial line and second is the equator line. We have to discuss the electric field intensity due to a dipole along both these axes or both these lines. So first of all, let's see what is a dipole. As already discussed, a dipole consists of a system of two opposite charges plus q and minus q separated by a small distance twice a. Now if we draw a line connecting these two charges, these two opposite charges, then that line is said to be an axial line. Similarly, if we draw a line which passes through the midpoint of the distance between these two charges, this is the midpoint here, this is the midpoint of the dipole, and if we draw a line perpendicularly passing through the midpoint, then that line is said to be an equatorial line. As already discussed in the previous class, the electric dipole moment is a vector quantity which can be described as q into twice a. Here twice a is the distance between the charges and q is the magnitude of any of these charges. Alright. So now our first task is to calculate the electric field intensity on the axial line of an electric dipole. So in order to calculate the electric field intensity on the axial line, which is this line, on the axial line of an electric dipole, we have to first draw the figure. So here I have drawn a plus q charge, here a minus q charge. The plus q charge is at the point B while the minus q charge is at the point A. We consider a point P which is on the axial line of this electric dipole AB. Right now, the separation distance between the plus q charge and the minus q charge is twice A, and we consider the point P to be at a distance R, from O, and here O is a midpoint of the dipole. So I have written here, let a unit positive charge be placed at a point at P at a distance smaller from O. So what we are doing here is we are placing a unit positive charge in order to calculate the electric field intensity. At this point we are placing a unit positive charge. Unit positive charge means plus 1 charge here at this point, which is at a distance R from the point O. This is the distance R. The diagram can be drawn in this way. So now you may ask me a question as to why I have taken a positive charge here. See, if we place a positive charge here, then what will happen? This will come under the effect of this dipole. Here the plus q charge will try to repel this charge, whereas the minus q charge will try to attract this charge, which is at this point. So what will happen? This charge will be under the effect of both these two charges. So as a result, at this point we can calculate the electric field intensity. Now how can we calculate the electric field intensity? First of all, you know that if here there is a positive charge and this is a positive charge, then this charge will be repelled by this charge, whereas this charge will attract this charge. So what we get is a force of attraction, a force of repulsion between these two charges, whereas a force of attraction between these two charges. That force can be calculated using Coulomb's law. So from Coulomb's law we have F equal to K Q1 Q2 divided by R square. Here K is the constant 1 by 4 pi epsilon naught. Q1 is the first charge. We may consider this to be the first charge. So this is plus 1, whereas Q2 is this plus Q charge. And the distance of separation, what will be the distance of separation between the charges? Now this we have seen that from this point to this point the distance is R, and again here O is a midpoint between midpoint of the dipole. So what will happen? The distance between this point and this point will be R minus A, whereas the distance between this point and this point will be R plus A. From if we get these two distances, then we can easily calculate the force between the plus q and plus 1 charge as well as the minus q and plus 1 charges. And from the force we can also calculate the electric field intensity at this point. what was the electric field intensity? First of all, we will have to calculate the electric field intensity due to discharge. Second, we will have to calculate the electric field intensity at this point due to discharge. So for the first charge, let us consider the plus q charge. For this charge, what will be the electric field intensity at this point? That will be E1 equal to F by Q. This is the charge. So we can see that we can easily calculate the electric field intensity at the point P due to both the charges of the dipole. So let's go to the discussion. First, we will calculate the electric field intensity at this point due to the first charge plus Q, due to the first charge minus Q. So I have written here the electric field at P due to the charge minus Q at A. We are going to calculate the electric field intensity at the point P due to the charge minus Q. The minus Q charge is at the point A. So what we will get the electric field at this point? We are writing that the first field as E1, the first field intensity as E1, which will be equal to KQ divided by the distance square. Now we have written the constant as K. What will be the first charge? Q. That is that should be minus Q. So we have put the minus sign outside. We have now we get KQ divided by AP square. Here this AP is the distance from here to here, which is R plus A. So we are writing here R plus A square. Now what will be the direction of the electric field intensity E1 due to the minus Q charge? See, we have already discussed that the direction of electric field intensity is given by the direction of force. So in whatever direction we are getting the force between discharge and discharge, that will be the direction of the electric field intensity. So here we can see that there is a positive charge at the point P and there is a negative charge at the point A. So what this minus Q charge will try to attract this charge. So as a result, we will get a force in this direction towards the minus Q charge. So what will be the direction of the electric field intensity? That electric field intensity we have written as E1, and its direction will be towards this direction. It will be along this direction. So we have written that the direction of electric field intensity E1 is along the direction PA, which is from here to here, along this direction. Similarly, we can calculate the electric field intensity at the point P due to the plus Q charge, which is at the point B. For this, we have written the electric field intensity at this point to be E2. This is the electric field intensity at the point P due to the charge plus Q, which is at the point B. So we have to use the same formula, E2 equal to KQ divided by the distance square. Now here K is the constant 1 by 4 pi epsilon naught, and Q is the charge plus Q. Here we have a positive charge, so there will be no negative sign. In the denominator, we have to put the distance. So what is the distance? BP, that is equal to R minus A. So we have written here R minus A whole square. What will be the direction for this electric field intensity, for the second electric field intensity E2? See, this is a positive charge and this is also a positive charge. So what will happen? This positive charge will try to repel this positive charge. So as a result, we will get this charge will experience a force which will be in this direction, which will be along this direction. So we can write the direction of E2 to be along this direction, or we can say that it is along BP. Here there is B and here it is P. So the direction of electric field is along BP, not in the direction PB. Is it clear? So what will be the total electric field intensity at this point? That is very easy. We can easily calculate it by adding the electric field intensity due to the first charge and the electric field intensity due to the second charge. So here we have to add E1 and E2 to get the total electric field at this point. So we have written the total electric field at the point P is E equal to E2 plus E1. If we simply put the values of E2 and E1 here, then what will we get? E2 was KQ divided, we got E2 to be KQ divided by R minus A whole square, and E1 to be minus KQ divided by R plus A whole square. So here we have seen that K and Q are common to both the terms, so we have kept K and Q outside, and inside we have 1 by 4 pi 1 by R minus A whole square minus 1 by R plus A whole square. If we take LCM for these two terms, then we'll get a formula like this. R plus in the denominator we'll have r minus a, r plus a whole square. I have combined these two, so that's why I have put a curly bracket here, and outside I have written for the whole thing I have written a power 2. In the numerator we'll have r plus a whole square minus r minus a whole square. Now if you break this part in the next step, if you break this part, then what will we get? A plus b whole square formula. So we have used that formula, a plus b whole square formula, and we get here r square plus a square plus twice ar. Here we have a minus sign, so I have put a minus sign. Similarly, putting the minus sign for all the other terms, we get r square minus a square plus twice ar in the numerator, and in the denominator we have r minus a into r plus a whole square. Here we can see that r square and r square gets cancelled out, a square minus a square gets cancelled out. What remains is only twice ar plus twice ar. So what we have in the numerator, that is 4ar. kq will be there, and in the denominator what we see is a plus b into a minus b. So we can write this formula as a square minus b square formula. So similarly here we have r minus a, r plus a. So what we can write here is r square minus a square. Outside we have a power 2, so I have written that power 2 here. Now if we reorganize this formula a little bit, then we can write it as kq into, if we reorganize this part, then we can write it as twice a into twice r. The term remains same, the multiplication, if we multiply these two terms, then we get this term. So we can write here twice a into twice r. In the denominator it remains the same, r square minus a square to the power 2. Now we can see here that q into twice a is the electric dipole moment. We have already discussed that q into twice a is the electric dipole moment, which is a vector quantity. So in place of q into twice a, we can put here p. What remains is k into twice r divided by r square minus a square whole square. Similarly, so this is the formula, this is a very important formula. This is the formula for electric field intensity at the point p. Now what will happen if the distance a is much less than r? That means the point p is at a very far distance from the point from the dipole, or we can say that the length of the dipole is very small compared to the distance r. So in this case we can neglect the a terms from the denominator. So here we will get E equal to kp, here it is kp into twice r remains the same. From the denominator we can neglect the a term, we can in comparison to r. So what we can write here is r square to the power 2, that will become r to the power 4. So this r and 1 r from the denominator will cancel out. So ultimately what we will have is kp into 2 divided by r cube. So from this we can see that the electric field intensity at the point p for a very small dipole whose length is very small, the electric field intensity varies inversely as the cube of the distance between the point and the midpoint of the dipole. So this is the electric field intensity on the axial line of an electric dipole. In the next section we'll have to discuss about the electric field intensity on the equatorial line of an electric dipole. Thank you.